This is a video about second order equations that have repeated roots. So I'm just going to try to describe what you do just through an example. So we're going to solve this initial value problem, x double prime plus 2x prime plus x equals 0 with the two initial conditions that x of 0 is 1 and x prime of 0 is 2. Remember, x is a function of t. So the value of x at 0, when t is 0, you get x is 1, and when t is 0, you get its derivative as 2. So how do we do this? Remember what we've been doing. We've been taking the equation that we're given, and we're looking for a, b, and c. So a is 1, it's on x double prime, b is 2, and c is 1, the thing on x. And what we're going to do is we're going to use that to make the characteristic equation. And so we're going to talk about this quadratic equation, lambda squared plus 2 lambda plus 1. That thing factors in this case. You get lambda plus 1 all squared equals 0, and that tells you get one root. So just lambda equals 1 is the root of the characteristic equation. Again, to tie this back in, if you were to rewrite this single equation as a system of two linear differential equations, what we're saying is lambda equals 1 would be the eigenvalue of the matrix. Anyway, we're not doing that, but it's always good to think about how this stuff relates to each other. So what do? You just get lambda equals negative 1 here. So, what do we know? Well, we know one solution is then x equals e to the minus t. We got a problem though. How do I get another solution in order to talk about what the general solution should be? And so, thus far when we've been solving these things, we've usually had two different exponential functions that will characterize what the general solution to one of these second order equations looks like. So what's the trick? How do we get another independent solution in order to put the general solution together? So what do I couple with e to the minus 2? All right, well, here's the trick. You're just going to multiply the answer that you got up there in orange, multiply it by t, and that'll form another independent solution. Pretty easy. So maybe you're wondering like, does that really work? Well, I read your mind and I worked it out ahead of time so I could show you. So what we're going to do is we're just going to verify really quickly here. This isn't something you'd have to do. This is just to convince you that like, oh, he's right, that will work. Okay, so does that really work? Well, why don't we plug in t e to the minus t for all the x's that you see? And that's what I've done in the second line here with the arrow. I replaced all the x's that I saw with t e to the minus t. And then I'm doing some of these derivatives. So let's see, for the first one here, there's a double prime on t e to the minus t right here. I'm just going to do 1 prime, and inside of there you need the product rule. So derivative of the first would be 1 times e to the t plus t times the derivative of the second. So that's just why that minus came down. But you notice, well, I've got to differentiate again. I'll do that in the next step. But anyway, there that piece is from single prime, and I just copy pasted this one there. So let's go ahead and do that last derivative right here. And so this minus will come down, and I've got to product rule this again. So when I do that, it looks something like this. After you have maybe distributed all your minuses through here, you should be able to regroup some of the stuff that looks like each other. And so what do I hope that you notice? The stuff in red adds up to 0, and the stuff in blue adds up to 0. And so we get 0 equals 0. And otherwise, yes, it's true that t e to the minus t works to plug in for x. When you add that all up, it truly equals 0. So we just verified that yes, this is a solution. Okay, so what do you do with that now? The general solution then is, just like it has been before, C1 times your first solution plus C2 times your second solution. That's it. That's all you got to do. So when you're doing these problems, again, you don't need to do this stuff in green. That was just to convince you that, hey, this really counts. That's really that's really an answer as well. And then these two things, they're not constant multiples of each other, so they're linearly independent. Therefore, they will make up the general solution. Now, that's part of what we're doing. If I scroll back up to the original question, we just found the general solution to this differential equation. Well, I want to know which one of those curves in the general solution figures out or satisfies these two initial conditions. So in other words, what are the values for C1 and C2 that'll satisfy those two initial conditions? So let's go on with that. Do all that in yellow here. So the first initial condition was x of 0 is 1. We'll just plug that in to the general solution here, and that would look like, okay, this says that x is 1, so that's why there's a 1 here where that x was, and then on the right side plug in 0 for all the t's, and out of that, this one's pretty nice, where that 0 here knocks out this entire term, and so you just get c1 is 1. They're not always going to be that nice, but at worst it's going to be some number times c1 plus some number times c2. So what do we do with the second initial condition? Well, the second conditional condition, if I can remind you, is x prime of 0 equals 2. You've got to look at your general solution here, and you've got to find what x prime is out of that. And so, unfortunately, yes, you do have to product rule that again. But, if you look at my work up here, I did it like 4 times up there. Nothing changes, so we'll just copy and paste it right there. So that, again, is the product rule applied to this piece because we're finding x prime. Now what you'll do, you know that x prime is 2 whenever t is 0. So that you'll plug that into, again, the derivative here. So the left side becomes 2, that's x prime, and then plug in 0 for all the t's that you see. And if you work that all out, you get 2 is equal to minus c1 plus c2. So in general, just to remind you, from these 2 that you get, each initial condition gives you an equation that involves your unknowns, your c1 and c2. Generally, you probably think of those as a system. In this case, it's nice though because one of the equations just tells you, hey, C1's 1. In that case, you can just substitute into the second one, and you should get that C2 has to be 3. Therefore, at the end of all this, what do you get? Just plug those numbers in for C1 and C2. From your orange equation here, I'm saying replace that by 1 and replace this by 3, what I've highlighted in purple. And that's exactly what I've done to get the solution to the initial value problem. In other words, this is the curve that satisfies those 2 conditions. It goes through the point 0, 1, and its derivative at 0, its slope at 0 is 2. That would be this curve.